In today's video, we are going to be working on simplifying radicals. Before we do radicals, I want you to quickly graph this cube root using transformations. So I set up your parent function already on the left-hand side there. Please pause it for a minute, graph it with transformations. It just truly should take you a minute to go through it. Unpause it and I'll work through it. So when I go through and I look at my transformations, I look at what's affecting my x. What's affecting my x? It says plus 2. So all of my x values are going to do the opposite, which is subtract 2. So negative 8, negative 3, negative 2, negative 1, positive 6. And then my y value, what's affecting my y value, is the multiplying by 2 and the subtracting 1. Since it's on the other side, it's the same operation. So I take my y value, negative 2, I multiply it by 2, and then I subtract 1. So my y column is going to be negative 5, negative 3, negative 1, 1, and 3. With cube roots, we have that turning point. The turning point is usually 0, 0. In my transformation, 0, 0 became negative 2, negative 1. That is a huge, important point. From there, your turn is going to change, so make sure you have that correctly listed. So now I'm going to graph the rest of my points, negative 10, negative 5, negative 3, negative 3, negative 1, positive 1, and 6, 3. From that turning point, up and out, down and out. And there's your graph. Okay, so if you struggle with doing the transformation piece, you really should just start with your parent table and come to your transform table, plot those points, and you have your graphs. Square roots and cube roots both work the same way. Okay, so now we're going to get into simplifying radicals. We're going to go through quite a few examples of simplifying radicals. Some of them should be very familiar to you. You've done them before. Others of them are going to be a little bit different. We are not limiting what kind of roots we can look at. We will be looking at square roots, cube roots, sixth roots. Any kind of root we want to look at, we will see. So to begin with, we can break down 128. So I'll figure out what perfect square, because it's a square root, what perfect square goes in 128. So it's the square root of 64 and the square root of 2. Square root of 64 is 8 times the square root of 2. Now maybe you didn't see right away that 64 worked. Maybe instead you're like, okay, I know the square root of 4 goes in there. 4 easily without a calculator, you can see goes in there, and what's left is 32. Well, square root of 4 breaks down to 2, of course. 32 then, maybe now you see easier that 16 goes in there with 2 left over. So that's 2 times 4 times the square root of 2, which is just 8 square roots of 2. Again, same answer. One other way that you can look at seeing these, and this might be helpful when we start looking at higher roots because you usually know your square roots, break this down with your factor tree. 2 and 64, maybe then you'd go 8 and 8, 8 and 8's 4 and 2, 2, 2, 2, 4, 2, 2. Since it's a square root, you can combine together doubles. So here's 2 2's, here's 2 2's, here's 2 2's, and then there's this one left over. So if I look at 2 times 2, well that's 4, square root of that is 2, 2 times 2, this pair here, square root of that is 2, and then here, and then I have this lone one, it doesn't have a partner, which is still going to go under the radical. So 2 times 2 times 2 is 8 times the square root of 2. Again, square roots, you probably know them a little bit more. You're less likely to use this third option. But then we're going to move into cube roots. In cube roots, you now need to know your perfect cubes, or again, use that factor tree piece. So you may wish to make a list until you get comfortable. 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. You might not be quite as familiar with these because we don't use them as much, or up until now we haven't used them much. So I have to figure out now what perfect cube goes into 128. Well, if I look in here, 128 is divisible by 64. So it's the cubed root of 64, and 64 times what gives you 128? Well, that's just 2. So this is 4 cube roots of 2. The factor tree does come in helpful here. So 128, we did this before, real quick. Because it's a cube root, now I'm going to group 3's. So here's one grouping of 3, here's one grouping of 3, and then whatever's left over is still underneath the radical. So the 2 is what's underneath the radical, and then here's one group of 2, and here's another group of 2, and times the cubed root of that 2 left over, which gives me the same answer. So just breaking them down, however you need to break them down, it doesn't matter as long as you can get them there. We can do operations with radicals. We can add them, we can subtract them, we can multiply them, divide them, etc. So if I'm going to add them, I have to have the same thing underneath the radical. These two pieces have to be the same, and whatever the root is, those two pieces have to be the same. So in order to try to even do this, I have to break down my radicals. We already know the square root of 128 is 8 square roots of 2. So now I have to break down the square root of 18. That's just the square root of 9 and the square root of 2. So that's 3 square roots of 2. So they both have the exact same thing attached. They are both square roots of 2. So I have 8 square roots of 2 plus 3 square roots of 2 give me 11 square roots of 2. If one was a square root of 2 and one was a square root of 3, I couldn't combine them. I'd be done. That would be as simplified as I could get. Next thing we have to work on. So what we were working on before is breaking down those radicals into as small as possible. The next thing that we can't have with radicals is a radical in the denominator. It's called rationalizing our denominator. I can't have the square root of 2 in the denominator. So what I have to do is, it's an expression, remembering back to the last unit. So I can multiply by a form of 1. That form of 1 I'm going to multiply by is so that when I take the two denominators and multiply these two pieces together, I end up getting a perfect, in this case, square, because it's a square root. So I have to figure out, okay, 2 times what number, again, it's a square root, 2 times what number is going to give me a perfect square? Well, 2 times 2. So I have on the top the square root of 2 over the square root of 4. Because it's a square root here, it's 4. Oop. And the square root of 4 is just 2. So when I rationalize my denominator, I get the square root of 2 over 2. It looks uglier than the first problem, absolutely, but it is rationalized, which actually helps simplify things out, especially if you're not using calculator. It's hard to take 1 and divide it by the square root of 2. It's a lot easier to take the square root of 2 and divide it by an integer. We're going to keep working on some of these simplification pieces, but just so that we have common working knowledge of information, I already called this n a root. It's also called the index, square root, cube root, etc. It's the index as well. This part here, this bar, is of course the radical. And this part that's underneath here is called the radicand. Radicand. Okay, so that you know when I start talking about the rules for simplifying radicals. So we have 3 different rules for what's called simple radical form. The first one, the radicand of an nth root contains no nth powers as factors. You may want to pause this and get them written down. I'm going to go through a couple of quick examples with each of them. So it can't have any nth roots as factors, or nth powers. So for instance, the square root of 8 is not simplified because there's a perfect square underneath here, so we have to rewrite that as 2 square roots of 2. The second one, the root index is as low as possible. Situation for that would be the 4th root of 9 is not simplified. The 4th root of 9, if you go back to our exponent properties, that's the same thing as 9 to the 1/4. And 9 is 3 squared to the 1/4, which is 3 to the 1/2. So the 4th root of 9 is actually the square root of 3. If you're breaking down your index, you are going to go and write it as an exponential. No radicals in the denominator. I just showed you an example of that. That would be such as 1 times the cubed root of 5. So I'll do a cube root this time. Since it's a cube root, I have to multiply it by a cubed root of something over a cubed root of something. Now I have to go back and think about what my perfect cubes are. So back here we have all the different perfect cubes. So I need to figure out 5 times what number is going to give me one of those. My goal is a perfect cube. I'm not multiplying it by a perfect cube. My result has to be a perfect cube. So 5 does not evenly go into 8. 5 does not evenly go into 27. It does not evenly go into 64, but it does go into 125. It actually goes in there 25 times. So I'm going to multiply top and bottom by the cubed root of 25. Because now, what I end up with is the cubed root of 25 over the cubed root of 125. The goal was to get rid of the radical in the denominator, and we did, because the cubed root of 125 is 5. Please do the math to support that. Don't make an assumption that you're doing it correctly. Go through and do the mathematical support. So there's no longer any radicals now in that denominator. The next one, large radical in your denominator. There are a few different options for breaking this one down. 1024, first off, is a pretty large number. Okay, that's a pretty large number. So you may wish to rewrite this and try to break it down if you want. Break the radical down first before you get it out of the denominator, or you can get it out of the denominator first and then break down what you need to, because there's a few things that are going to take place in this problem. One thing that I might do is I might look at what are my sixths. 2 to the 6th, 3 to the 6th, 4 to the 6th, and see if any of those numbers go in there. Just that way I have a little bit of a smaller number to work with. So I'll start that way, and then I'll show you another way to do this one as well. So if I break down the 6th root of 1024, a perfect 6th is 64. That's 2 to the 6th. And then I have left over the 6th root of 16. So that's just 5 over 2 times the 6th root of 16. So that's one option. Okay, starting that way, at least bringing it down. Now I still have to get that radical out of the denominator. So I need to figure out, okay, what do I have to multiply 16 by to get a perfect 6th? Multiplying by a form of 1. So 2 to the 6th, 3 to the 6th, 4 to the 6th, etc. Get what those numbers equal. What I need to multiply by is the 6th root of, so 16 times 4 is going to give me 64, and we know 64 is 2 to the 6th. So this is one option. So now I have 5 times the 6th root of 4 over 2 times the 6th root of 64, which we of course know is 2. So this is 5 times the 6th root of 4 over 2 times 2, which is 4. So now it's rationalized. The last part that you have to look at is making sure that your index is as low as possible. So right now I have 4 to the 1/6, which is the same thing as 2 squared to the 1/6, which is the same thing as 2 to the 1/3. So my final answer for this is 5 times the cubed root of 2 over 4. Depends on mathematically what you can see as to how quick you'll be able to break some of these down. Some of them you may have to go a few extra steps in. Others of them you'll be able to see quite quickly. I'm going to do this one more way. So we have 5 over the 6th root of 1024. Just because this next one I'm going to show you might look simpler, it's not always simpler. You may have to try some things, a little bit of trial and error to see what's going to take place, what's going to make this as easy as possible. If I get stuck and I'm not quite sure what to do, factor trees work really well. 2 and 5, 12, 2 and 2, 56, 2 and 128, we're out of room here, 2 and 64, 2 and 32, 2 and 16. So therefore 1024 is 2 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2 to the 10th. And maybe you knew that already too. So that's the same thing as 5 over 2 to the 10th to the 1/6, which is 5 over 2 to the 5/6. Oops, 5/3, sorry. Since it's in exponent form, I need to get the denominator not to have a radical. So I have 5/6 right now. So if you can remember what we do with exponents, if I multiply by form of 1, I add exponents. So if I multiply both top and bottom by 2 to the 1/3, When bases are the same, I add exponents. So therefore, I have 5 times the cube root of 2, I'll put it back in radical form, over 2 to the 6/3, which of course is 2 squared, which means this is 5 times the cube root of 2 over 2 squared, which is 4. Same answer as before. So it's just another way to go through your process, trying to figure out what's easiest for you. Different people will see different things right away, so don't feel badly if it takes you a little bit longer than somebody else. It's just a process you need to go through. What we care about, that it's in simple radical form. Okay, next, this is just all multiplication. I have 3 cube roots of 4 times 2 cube roots of 2, which is really just 3 times the cube root of 4 times 5 times the cube root of 2. And it doesn't matter what order I multiply pieces in. So this is all multiplication. I can put a multiplication sign there, I can put a multiplication sign there. It's all multiplication. That's the same thing as 3 times 5 times the cube root of 4 times the cube root of 2. Coefficients get multiplied together, radical pieces get multiplied together. But the only way you can multiply radicals is if they have the same index. So I take 3 times 5, so I get 15. Since they're both cube roots, I can actually multiply them. Parts that are underneath get multiplied together, which gives me the cube root of 8. And the cube root of 8 is a perfect cube, which is 2. Therefore, my answer is 30. Part of the reason why this works is I can take this again, rewrite it exponentially instead of radically. This is 4 to the 1/3 times 2 to the 1/3. I have an exponent, the same exponent that's attached to each, which means I can pull that factor out. It's reverse sending it through. So this was a property, we usually started here and went to here, but we also need to be able to come back down, which then just gives me 8 to the 1/3, which takes me back to here, which is the cube root of 8. Okay, last problem. My denominator does not just have one radical in it. It is over subtraction, addition or subtraction, whether it's 2 radicals or a radical and an integer. You have to get rid of it. I can't just multiply by the square root of 5 over the square root of 5. If I multiply top and bottom by the square root of 5, I'm going to end up getting the square root of 25. Perfect, that's 5. Now I have minus the square root of 10. That doesn't help. Now if I try to multiply by square root of 10 over the square root of 10, I get the square root of 50. That doesn't break down. So no matter what, I'm ending up with radicals in the denominator. So if you are adding or subtracting in the denominator, because again, you have to get rid of the radicals there, you're going to have to multiply by the conjugate. If you remember the conjugate back to when we were doing quadratics and looking at complex conjugates, it changes the negativity. Everything else is exactly the same. So I have to multiply by the conjugate, which is root 5 plus root 2 on the top and the bottom. Because when I FOIL out my denominator, I need my middle 2 terms to drop out. So on the top, I have 6 times the square root of 5 plus the square root of 2, all over, I'll just show my work, square root of 25 minus, so outside, that's actually going to be a plus, is the square root of 5 times the square root of 2, which is square root of 10. Inside is minus the square root of 5 times the square root of 2, which is minus the square root of 10. And last is a negative. It's a negative times a positive. So it's a negative. Square root of 2 times square root of 2 is the square root of 4. Again, just showing my steps along the way. The most mistakes happen when you just make assumptions. Prove that you're right. Go through the actual processes. So this is 6 times the square root of 5 plus the square root of 2. All over square root of 25 is 5. These two undo each other. Minus 2, which is the square root of 4. So I get 6 times the square root of 5 plus the square root of 2 all over 3. This is kind of like in factored form. It's all attached by multiplication. 3 goes into 3 once, 3 goes into 6 twice. So it's 2 times the square root of 5 plus the square root of 2. And lastly, expanded out. These are not factors, they are radicals, which is 2 square roots of 5 plus 2 square roots of 2. So now we've gone through all of the different ways to simplify our radicals and to practice working with radicals. Everything that we're doing today is based on expressions. We are not working with equations. So please keep in mind, if you have to get rid of different pieces within the radical, the only thing you can do is simplify or multiply by a form of 1, because it's just simply an expression.